So I'll be talking about the program that we'll be organizing in summer 2025 on cryptography. So this is, with all these wonderful people, Dan Bonnet, Elliot Boyle, Shafi, Yuval Ishai, and Daniel Wicks. Okay, so modern cryptography was born as a subfield of theoretical computer science late last century, and essentially as a bridge towards information security. And for much of its early years, the focus was on secure storage and transmission of information. And over the last 2 decades, slowly with the emergence of new technologies, the focus has shifted towards the following 2 questions. The first is, how can we securely compute on data of users while maintaining the privacy of the data? And the second is, how can we verify that the computations that we perform on these data sets are actually correct? And there are basic questions about the assumptions that we need to solve these problems and how efficiently can we solve these problems. So to tackle some of these questions, in 2015, about 8 years ago, a program was organized at Simons Institute on cryptography, which was a tremendous success. Based on the reports that I saw, there were roughly 185 reported research papers, including many breakthrough results. And in fact, many subsequent breakthroughs that have happened in cryptography in the last 8 years can be traced back to the foundations that were laid down in this program. And the program was had a high participation and lots of activities. So building on the success of this program, and again, all the activities that have happened in cryptography in the recent years, we are organizing a new program in cryptography in 2025. So this program will have 3 main themes. The first theme will be program obfuscation. The second will be secure multi-party computation, and the third will be proof systems. I'll talk about all of these 3 programs shortly. And then the program will also have several parallel themes exploring, the connections between theoretical CS and cryptography, quantum cryptography, something Sandy already talked about, as well as other topics like low complexity crypto. I just didn't have a better picture, so I put Yuval's picture here as a representative of this area. So let me talk a little bit about the main themes. So the first theme is program obfuscation, which is essentially a technique for taking a computer program and converting it into a new program, which is completely unintelligible. That is, you cannot reverse engineer it. You cannot figure out what are the internal details of the new program. And this is essentially a great tool to hide secrets within programs. And as you can imagine, this is an amazingly powerful object. Obviously, it has applications to topics like software watermarking, but it also has many applications outside cryptography in theoretical CS, such as establishing hardness of various complexity problems, differential privacy, meta complexity, and more. And in some sense, we widely believe that obfuscation is so powerful that it's essentially crypto-complete in the sense that most cryptographic problems can be solved using program obfuscation. So there has been a lot of activity in this area in the last 8 years or so. After a long line of research, we now actually have general purpose obfuscation from well-studied assumptions. So this has been a major breakthrough that happened 2 years ago. But despite all this progress, this area is still pretty much in its infancy in the sense that while we have now constructions from well-studied assumptions, we still don't know a lot in this area. So for example, we don't know how to build post-quantum solutions, so solutions based on assumptions that cannot be broken by quantum computers. Current constructions do use some assumptions that can be broken by quantum computers. The efficiency of the current solutions is terrible. They are not even close to implementable, so there's a lot to be done in that regime. And we also have open questions with regards to the kind of security properties that we can achieve. Okay, so the second topic is secure multi-party computation. This is essentially a way for a group of parties to jointly compute on their inputs while maintaining the privacy of their inputs. That is, the participants only learn the output of the computation and nothing else. You can also think of MPC as essentially a way to eliminate single points of failure in a distributed computation. Sort of an analogy can be drawn to error correcting codes now in the context of distributed computation. So for this reason, secure multi-party computation is very, very useful in building decentralized systems. That is where you can distribute trust amongst multiple parties and allow them to compute on their private inputs has lots of applications. I'll just point out applications to federated learning where this model seems to be quite useful. And again, there has been lots of progress in this area. Before 2015, we only knew how to achieve sublinear communication, that is, allow parties to compute on their inputs such that the communication is sublinear in the size of the computation. We only knew how to do this using the general tool of fully homomorphic encryption, but now we can actually do it even without fully homomorphic encryption, which is amazing. We can even achieve sublinear time computation in some functionalities, such as private information retrieval. Back to FHE, we have had lots of efficiency improvements in this area, and we have also made progress in settling open questions related to minimal assumptions for MPC. But still, many open questions remain in this area, both on assumptions and efficiency front. The third theme, the final theme that I want to talk about, it relates to cryptographic proofs. So this is essentially similar to mathematical proofs in the sense that a prover can prove a claim, the correctness of a claim to a verifier, and we have standard soundness property that if the claim is false, then the prover should fail in convincing the verifier. What makes cryptographic proofs stand out is their ability to have seemingly magical properties. The first is that we can make proofs very, very short, even smaller than the size of the NP computation in this example. And the verification can also be very, very fast. So this is called succinctness or succinct proofs. And the second property is zero knowledge, which basically says that the proof reveals nothing beyond the fact that the statement is true. So again, as you could imagine, these such proof systems have lots and lots of applications. The signature schemes that we currently use in practice, most of them have their roots in cryptographic proofs. If proofs are small and they're efficient to verify, it also allows us to delegate computation to cloud computers, and then we can actually verify very quickly that the computation was done correctly without having to redo it ourselves. And again, the fact that the proofs are small and they also maintain privacy of the witness has lots of applications in blockchains. So in this area, a lot of progress that happened in recent years primarily focused on the setting where the proofs are one message. So the prover just simply sends one message to the verifier who can verify it, similar to mathematical proofs. So now we actually know how to build non-interactive zero-knowledge proofs from assumptions that we didn't know for a long time. So for example, we even have non-interactive zero-knowledge proofs that are post-quantum secure. We can also build succinct proofs now from standard assumptions for many subclasses of NP, something we didn't know for a long time, but now we can do it. And in the efficiency side, there are now numerous practical constructions of these objects which are actually used in practice. In fact, many companies, startups are focusing on this area because of the tremendous success that has happened. But there are still many open questions with regards to assumptions and efficiency. For example, can we actually make them so efficient that we can just make programs self-certifying? Program can prove that it's not a malware, right? That would be amazing. So I want to take a step back and just mention that while cryptography in general has enjoyed a strong synergy in the theory and applied side, this has only improved in the recent years. Again, just due to the success that has happened, the publication rate of crypto papers in security conferences has only increased. There are more and more programs from government agencies and private companies for supporting accelerated transition from theory to practice. In general, there's just more awareness in cryptography, which is great. And again, because of all of this success, there's a improved synergy in the academia and industry worlds. More and more companies, focusing on cryptography-related products, both in the setting of cryptographic proofs and also in the setting of MPC, FHE, and so on. So hopefully, to build upon all of this success, we'll be able to build upon this success in the cryptographic program in 2025, and hope to see you in the near future. Thank you.
Thank you. And we will take a quick break and we can convene in about 15 minutes.